So first of all, I'd like to thank the organizers for inviting me here to the IOTime conference. It's been very nice. Thank you very much. So the work that I'm going to be presenting to you was all done by my former graduate student, Abhishek Yadav, who's currently has a faculty position in a university in Gujarat. This was a collaborative work with John Hench. And I would like to acknowledge Trinity College, Cambridge, which enabled my visit to Cambridge, and the Gyan Scheme of Government of India, which enabled John's visit to IIT Bombay. So before I get into the talk, I thought I'll just present to you some of the other work that we're doing. One of the main areas that I work in is in the stability of thin liquid sheets, which is related to the problem of atomization of liquid. And there we are interested in understanding the mechanism of breakup of thin liquid sheets into fine droplets with the objective of, in fact, controlling the final drop size distribution. There are many such examples. So in this particular case, you have a pressure swirl nozzle out of which a liquid sheet is coming out. It's a hollow cone, expanding cone. And then it flaps and breaks up into fine droplets. You can create such sheets, in fact, flat sheets, in the laboratory by impinging two water jets. And so I have two movies of that. So the one on the top is at low speeds, which leads to this liquid sheet that forms. Water collects at the rim. It's more or less a smooth sheet. And then the drops break up from the rim, and then the size of the drops is approximately the same order as the thickness of the rim. If you increase the speed of the liquid, then you no longer have a coherent liquid sheet. It starts to flap, it breaks up into ligaments, and then you get much finer drops. So we're trying to understand the physics so as to finally control the final drop size distribution. The other area that I work in is colloidal films. And the goal there is to understand how, starting from a dilute dispersion of colloids, this could be large and small particles of different shear moduli. If you apply a film on a substrate and when the solvent evaporates, particles consolidate, they may deform if these are soft particles like polymer particles, and then coalesce to form a film, or in some cases, in fact, the stresses that develop could crack the film. And we are interested in understanding the physics right here so as to get an improved performance of coatings, ceramics, and so on and so forth. So what I'm going to be presenting today has nothing to do with the two areas that I showed. It's a new problem for us, and we are still trying to understand that. So I'd like to start by showing you the experiments that we've done. So we built this experimental setup, which essentially consists of two parallel wires. The diameter of the wires is approximately 200 microns. It's not very important. They're placed at a distance of about 4 millimeters. Okay. On the other two sides, we have these plastic blades which gently sit on these two wires at a distance of about 8 to 10 millimeters. Okay. So here is a photograph of the same. These are the two wires. These are the two big blades. This entire setup is put on an inverted microscope, and you can see the objective here at the bottom, and we look at what happens here. And what is in between these wires and blades is a thin liquid film which is freely suspended. Okay. This is essentially an aqueous film. This is just the water, which contains a very dilute concentration of polystyrene particles of different sizes. So each experiment, well, I'll show you a mixture of particles, but essentially we have particles of sizes of 3 microns, 5 microns, and 10 microns. Okay? Now this entire setup is exposed to the atmosphere, so the water evaporates, so the film thickness changes in time. The initial volume of this film that we cast on the wires, somewhere between 5 to 8 microliters. What it means is that the average film thickness is about 100 microns. Okay. And so we're looking from the bottom using this microscope, and this is what we see. So we are in fact focusing on the central area in between the two wires and the blades. So I'll play the movie. You see that the outer particle is moving a little bit, but then there's this some violent motion where entire crowd of particles is pulled in, and the particles start to assemble into a ring right here. Okay, I'll play this again. You can watch the motion more closely. So nothing happens initially, but then after some time you start seeing these particles getting pulled in. It's quite a violent motion. It's a very rapid motion of particles. You form a ring, And in fact, there are no particles at all right here. Okay? When I say a ring, what really is happening is that you form this band or a ring of particles, which I try and show schematically here. So we are only seeing a section of that with almost no particles at the center. Okay. So of course the question is, why do we have this rapid inward motion initially? Because particles started moving in this way to form a ring, and why is there this slow outer motion that takes place? Okay. So here's another movie where we have a mixture of 5 and 10 microns. Okay. And this is taken with a lower numerical aperture objective lens so that you can see a wider region. And here what happens is that there's a mixture of 5 and 10 microns. The 10 microns first form a ring. Nothing really happens to the 5 microns. I don't know if you can see, but then after some time, you see that they start moving in and then move out slowly and form a ring. Yeah. So what happens first is the larger particles are the ones that get pulled in, and then they move out. They form a ring, and as they move out, they collect these large particles outside as they move out. Nothing happens really to the 5 micron particles. The 5 micron particles also, after some time, they move in at a very high speed, and then they move out. As they move out, they form this ring, and then they start collecting the 5 micron particles. So in fact, particles are being separated by size. And again, although it may not be clear from where you're sitting, there are almost no particles here at all. So we are actually separating particles by size. So why is this happening? Well, this is an intriguing phenomenon. I would like to understand what is causing this kind of a motion and separation. But understanding of particles and interfaces has a number of applications in the industry, and I have only listed a few. For example, in the food industry, what I show here is from a publication by Gozenbach et al. It's a model cream, a whipped cream, which essentially consists of air bubbles which have been stabilized by these silica particles. Here's a confocal microscopy of a part of this cream, and what you can see here is about 50 to 100 micron air bubbles which have been stabilized by these silica particles. Okay. Then we have, of course, mayonnaise, where these egg yolk lipoprotein granules stabilize the oil in water emulsion. So these are Pickering emulsions. In the mining industry, in the froth flotation process, where at the bottom here we have an agitator which creates or generates bubbles, and as these bubbles rise, the fine minerals attach to these bubbles, and then they are collected on the top. Okay, and so this is in air in water kind of an emulsion. Then in case of a removal of oil spill, so when you have an oil spill, this oil is broken down into fine droplets by wave action or water motion, and these tend to get stabilized by suspended particles. And this is good because this leads to a faster biodegradation by the microbes which are there in the medium. In all of this, one of the most important criteria or the parameter is the contact angle that the particle makes at the interface with the two phases. Okay? So if you look at a spherical particle, let's say at a water oil or a water air interface, then the contact angle that this interface makes with the particle on the water side, which is what I will call it the contact angle in this particular case, is less than 90 degrees. We know that the particle likes to stay more in water than compared to the oil phase. So majority of the area of the particle will be on the water side. Yeah? And when the angle is equal to 90 degrees, half of it will be in water and the other half will be in air or oil. When it is greater than 90 degrees, then majority of it is now going to be in the oil phase. Consequently, particles which have a contact angle less than 90 degrees, which are hydrophilic particles, tend to stabilize oil in water emulsions, and that's because now majority of the area is in the continuous phase, which is the oil phase, which is the water phase in this case. When you have angles greater than 90 degrees, they tend to stabilize water in oil phase because now the particle wants to stay more in the oil phase. We all know this, that the energy for removal of a particle from the interface is extremely, extremely high. The expression for this is given here. In fact, we'll go through the derivation for this later because it will be important for this problem. So the energy required to remove it would goes as R squares times gamma LV, which is liquid vapor interfacial tension. And you have a cos theta. You have a plus and minus depending on in which particular phase you want to remove the particle into. But if you put in the numbers for a 1 micron particle, it tells you that the energy for removal is extremely high. It's about 10 to the power of 7 kT. Okay, so once the particle is absorbed at the interface, it's very difficult to remove it. So before we go ahead, it's important to do a dimension analysis of the problem and look at what forces are important. And so for the kind of motion that we observed in our experiments, when the particles rapidly move in before they move out into a ring, the velocities are of the order of 0.1 to about 1 millimeter per second. The radius of the particle varies in our experiments from about 3 microns to 10 microns, so that's the range. The interfacial tension 0.03, about 0.1 Newton per meter. And the viscosity of water is what I've used here. And so the first number to look at is the Bond number, which is the ratio of the gravitational force to the interfacial force. We find that that number is very small, and therefore buoyancy is not very important for our problem. The particle inertia is also negligible because the Reynolds number is very small for the kind of motion that we have. The capillary number, which is the ratio of viscous forces to the surface tension forces, again is very small. Now, this does not mean that the viscous forces are not important. What it means is that the interface shape is decided by the instantaneous position of the particle. So if the particle moves, the interface will change its shape almost instantaneously to adjust to the new boundary conditions. That's what it really means. Particle diffusion, well, diffusivities are very small for these particles, and so Peclet numbers are large, so we can forget about that. And if we look at problems where the interfacial slopes are very small, then the Young-Laplace equation is the following in the non form, where zeta here it tells you the position of the interface with respect to some axis that we have. Delta P is the pressure difference between the liquid phase, say the liquid and the air phase. Gamma is interfacial tension, R is the radius of the particle. So here we have made the small slope approximation. Okay, so let's start with this simple case. Many of you might know this, but as I said before, this is important for the current problem of a single particle at a flat interface. So we start with a particle, a solid particle, let us say, which is present in the vapor phase, and here is the vapor-liquid interface. We ask the question, what is the energy change when we move this solid particle from the vapor phase to the interface? Okay. So the initial interfacial energy is essentially the surface area of the solid, 4 pi r square, times the interfacial tension, which is gamma SV, plus the surface area of the vapor-liquid interface, which is ALV, times the interfacial tension of the liquid-vapor interface, right? Now, when we bring the particle to this particular interface, our energy is going to change, the surface energy is going to change. So first is the energy of the vapor-liquid interface, that is going to change. It's going to be its initial area minus the area of this disk, which has now been removed, and that is given by this particular term. Next is this extra energy that has come in, which is the liquid-solid interface, which is going to be 2 pi r square, which is the surface area of the hemisphere, plus this extra little bit, which is given by that. Whereas the energy of the solid-vapor interface has reduced, which is the hemisphere minus the same extra bit, which is given here. Okay? So the difference between this final energy and the initial energy gives me the net change in energy when I bring the particle from one of the phases to the interface. And if now differentiated with respect to zeta, with zeta here is the position of the interface with respect to the center line, which, or this, when I say center line, this is a line going through the center, right here, and equated to 0 to find out the equilibrium position. What it tells you is that the equilibrium position of the particle is going to be R times the interfacial tension between the solid vapor minus that for solid liquid divided by the liquid vapor, and this particular term in the square brackets is nothing but cos times the contact angle, which is there. So it really tells you is that if you take a particle and put it anywhere at the interface, the particle is going to move such that it reaches the equilibrium height, So that the angle now that the straight interface makes with the solid is the contact angle. And so now you find out what is the energy that is required to move the particle out from here to one of the bulk phases. You get that expression that I had. And so if you put 10 microns here, it goes the square of r, and so you have 10 to the power of 9 kT. Okay, we are interested in particles in very, very thin liquid films, in which case not just one interface, two interfaces will now become important. And so the past studies, when they have looked at such cases, for example, studies in foams, they have always considered constant thickness films. Okay, so here is a case when particle is now adsorbed simultaneously to both the top and the bottom interface. And let's assume that it's adsorbed in a very, very thick liquid film. And it's a hydrophilic particle, so theta is less than 90 degrees. So in this particular case, what would happen is that if the contact angle has to be satisfied at the interface, so instead of having a flat one, let's assume that it does satisfy. In that case, what is going to happen is that you're going to have a curved interface the way I have shown it, due to which now you're going to have a higher pressure in the liquid phase around the particle compared to the bulk, which would mean that it's going to drive the liquid out till the interface becomes flat. Now, with further liquid draining out of this film, one could probably reach this kind of a state where now the curvature is in the opposite direction, in which case it's going to pull the liquid out from the bulk towards the liquid, and this therefore is going to try and always bring in the liquid, and therefore it's considered these hydrophilic particles or with theta of any value less than 90 degrees should stabilize a foam. Okay. On the other hand, if you have a hydrophobic particle, what would happen is that this curvature is always going to be the same. Well, the sign is always going to be the same, in which case the liquid is always going to be pushed out from close to the particle till the film actually pinches off. And though it's always been thought that hydrophobic particles would always destabilize these thin films. That is, when both the interfaces are bridging, or the particle is bridging both the interfaces. But if you look at the experiments, they tell a very different story. So these are experimental results from the group at University of Hull. And what they did is the following. They took a container of a known volume and created a foam inside it by shaking it. Okay? They did experiments with particles and without particles and determined the time required for the initial volume to reduce to half its value. It's like the half-life of the foam. Okay? So they determined the half-life with particles, they determined the half-life without particles, took the difference and divided it by the half-life of no particles. Now if the particles were to stabilize the foam, this particular quantity on the right-hand side would be positive. If it destabilized the foam, this quantity would be less than 0. So here are the experimental results that they did with glass spheres, which were surface treated so as to change the contact line. Also contact angle, sorry. And there was some surfactant in here. Okay? So what you find is that for contact angles less than 75 degrees, where that simple picture of constant thickness film should have stabilized the foam, there is no effect whatsoever of the particles. You can see that this half-life ratio given by this definition is very close to 0. Once the angles increase beyond 75 degrees, you see a rapid increase in the stability of the foam. It does peak close to 90 degrees, and as expected, just beyond 90 degrees, it falls very quickly, and after which it destabilizes the foam. Okay? And so what they observed in the experiments is that there were very few particles in the solution. Almost all the particles were at the interface, and some of them accumulated the plateau borders. And their explanation was that probably the presence of the particles in the plateau borders reduced the drainage of the film, drainage of the liquid from the foam. The question now is, why is there such a sudden change at 75 degrees, or a sharp change in 75 degrees? So what they did is to plot this interfacial energy divided by pi r square. This expression is already right here. And so they plotted this as a function of the contact angle. So when your contact angles are less than 90 degrees, it's favorable to pull it, let's say, into the water phase. If it's greater, it's favorable to pull it on the oil side or the air side. So when you plot that, you find that at around 75 degrees, this particular energy falls to about 50%, in fact 55% at about 75 degrees. And so their explanation was that, well, the energy falls to almost half its value, and therefore probably it's quite easy for the particles to be swept away from the interface into the bulk. Okay? And that's the reason maybe why the particles are not stabilized at the interface. But really the order of magnitude of this energy does not really change. You are at 10 to the power of 9 kT, it's just 0.5 times 10 to the power of 9 kT. So we think that this is not a very convincing argument. In fact, if you just change the size of the particles by 70%, reduce it 70%, you should be getting a similar energy, but you still see significant stabilization. So we think that this problem or this issue is not fully resolved. Okay. What about emulsions, the so-called Pickering emulsions, where particles stabilize emulsions? So this is a classic work by Shulman and Lea, 1954, where they took barium sulfate powder and introduced it in a water-benzene surfactant mixtures. And there too they observed, well, they were able to change again the contact angle of the particle with respect to water. They found that when this contact angle is slightly less than 90 degrees, they tend to stabilize oil in water suspension. This is what we would expect. Less than 90 would mean majority of the particle would like to stay on the water side, and so it stabilizes oil in water emulsion. When theta is slightly greater than 90 degrees, they stabilize water in oil emulsion. And when theta deviated greatly from 90 degrees, it did not stabilize any emulsions at all. Okay? But again, when you look at the explanations that are given for the stability of such emulsions, there are many different mechanisms. But one of the mechanisms that is used is very similar to what I showed for foams, that you have the droplet phase on one side, you have the droplet phase on the other side, right in between you have this thin film, and therefore your contact angle is pinned. As you remove the liquid from this film, that is when the drops tries to come close together, this is how the interface is going to be. Your pressures are going to be low here, it's going to suck in the liquid and stabilize the film. Okay? But this should be true for, let's say, for all contact angles less than 90 degrees, but again the experiments tend to show that it has to be close to 90 degrees on either side. So that's the motivation. One of the main things, motivations is, the question is, why is this stability achieved when theta is close to 90 degrees? The emulsion stability that many have studied has required a very large density of particles. In fact, in full coverage of the droplet is what gives the stability, because of steric hindrance. When the particles come together, this monolayer of particles pushes the drops apart. But then there have also been experiments where stability has been achieved with a very, very low coverage of the surface with particles. In fact, what they have observed is that when the two particles come together, you suddenly find a high concentration of particle at the point where the two drops are trying to come together. And they observe that this tends to prevent the two drops from coalescing. And then the particles move away. And so the question is, this very strange behavior that we have seen in our experiments, can it shed some light? Probably not explain everything that is observed, but can it give us an indication as to what could be happening around 90 degrees or so? Okay, so the experiments that I showed you were earlier done in simple bright field microscopy. So we thought that in order to get a better understanding of what's happening, let's do it under a monochromatic light so that we can see interference fringes. Because if you recall, when we put particles of two different sizes, 5 and 10 microns, they in fact segregated. The 10 microns came in first, they formed this ring and then started moving out. And after that, we had the 5 micron particles showing the same strange behavior. So we thought that since particle size is involved, probably it has something to do with the thickness of the film. So we thought that let's try and determine that. So in the monochromatic light with the laser, what we found is, of course, these interference fringes, which tells you how the film thickness changes as we move from one location to another. I don't know how clearly it is visible here. These are the interference fringes. You see these alternate bands which are dark and bright. Please ignore these vertical bright lines that you see. It's an artifact of the confocal microscope that we are using. So I'll play this movie and you can see that motion in the presence of the fringes. So you moved in, And when they move out, in fact, they all collect on one particular fringe. Okay, let me play this again. And what you will see is that as the particles start moving out, there are particles which are outside that particular fringe getting sucked in. See, as this moves, this one gets sucked in, then these ones will get sucked in there. That one that got sucked in there. Right? And so here are snapshots from the same experiment, which probably are clearer than what you see there. So this is the initial position, let's say at time t equal to 0, and within a fraction of a second, you see that the particles close to this center have actually collected in, and then they start moving out, collecting into a band, and then after some time, you find that there are no particles at all in there. So velocities, when this rapid motion, when they move in, is of the order of 0.1 to about 1 millimeter per second. We can in fact determine what the evaporation rate here is, because if we sit at one particular location and determine the time required for the next fringe to move through, we know what is the thickness difference between one fringe and the neighboring fringe. We know the time difference. You take the ratio, it tells you the rate at which the water is evaporating. And we find that the evaporation rate, at least in the region of interest, is the same everywhere. Okay. So you can do these experiments. Now instead of 2 particles, you can do it with 3 different sizes particles. And here's a snapshot from such an experiment. You will first form the 10 micron ring. Particles come in, they form this ring, they start moving out. As they keep moving out, they collect the 10 micron particles. Same next happens to these 5 micron particles, then to the 3 micron particles. And there are no particles whatsoever in the center. Okay, so it's clear that the particle size is getting influenced, is influencing the phenomena. It's also clear that there's a variation in the thickness of the film because of, you can see how the spacing between the interference fringes is changing. So can we determine what the thickness is? But theoretically, making the small slope assumption, the curvature of the interface, either the top or the bottom interface, is equal to difference in the pressure divided by the interfacial tension. Okay, this is a dimensional form, the Young-Laplace equation, small slope assumption. Now, there is no bulk flow, which means that the pressure anywhere inside the film is the same. So if there was a pressure difference, we should have seen large bulk flow driving the liquid. Since the pressure is the same everywhere inside the liquid, outside is atmospheric pressure, although the interface is curved, delta P has to be constant, or has to be same everywhere. So what it means is that delta P by gamma is a constant, and therefore it means that the curvature of this interface has to be constant, top and bottom. H is the thickness, the local thickness of the film, and therefore I can solve the left-hand side of this equation. And if you do that, it tells you that the thickness at any given location minus the thickness at the center should go as r squared, with the coefficient being 2 times the curvature of the interface. Since we know the location of each of these interfaces, and we know therefore the difference in the thickness between the neighboring interfaces, which is given by lambda, which is the wavelength of light, divided by 2 times the refractive index of the liquid. We can plot h minus h naught as r square. These empty circles are experiments, and you can fit it with a straight line. And as expected, it is indeed a straight line. And the coefficient here is nothing but 2 times the curvature of the interface. So you can back out the shape of this particular interface from these experiments. So the question is, what is happening? So just to recall, we have these motions in 2 different directions. One very quick motion which comes in, and then the particles slowly start moving out. Right? So not only do we have motions in 2 different directions, but we have motion of 2 different speeds that is taking place. So here's what we think is happening. Yeah? So initially in the bulk, when you have a very thick film, particle is adsorbed either at one interface or it's in the bulk. At some point, it comes in contact with both the interfaces. Now let's consider this particular liquid film, which has a flat interface. Curvature is 0, but the thickness is actually varying, the constant slope. There will be one particular location where, when the particle is adsorbed at the interface, the angle that this flat interface makes with the particle will be indeed the equilibrium contact angle. Right? Okay? And that should be true for both for the top and the bottom interface, assuming that the center of the particle is going to be present at the center of this film. Because if I try and pull the particle up or down, then the contact angle will not be satisfied at one of the interfaces. It's going to be pulled down or up in the opposite direction. If I take this particle and pull it to one particular, let's say this location, and assume that it is pinned out here, then the angle it has to satisfy has to be the contact angle, and therefore the interface has to bend the way that I have shown here. So these blue dashed lines tell you the direction of force that will be acting on the particle. So if I collect all the forces, essentially get the resultant, that will be this blue dashed line. I can resolve it in the vertical, in the horizontal direction, and I would have the same thing at the bottom. The vertical forces will cancel, leaving behind a net horizontal force pushing the particle towards its equilibrium position. The same thing is going to happen if you take this particle and pull it to position C, where now I'm going to have a restoring force towards the equilibrium position. Okay? That was a force argument. You can do a similar thing with the energy argument. I have already shown you this particular slide, where for a single interface, I differentiated a change in energy with respect to this zeta to find out what the vertical position will be. In my case now, when you have the two interfaces, and when the particle is bridging both the interfaces, this zeta is going to change in the radial direction. So now I'm going to take the derivative of this with respect to r to get this restoring force. Right? And the expression is given right here, which is now this force is proportional to the difference between that zeta at that location and the equilibrium location times the slope of this interface, which is related to d zeta by dr. So what really happens is the particle initially, let's say, is absorbed at only one interface, and as the liquid starts to evaporate, both the interfaces start to come together. At some point, let's say at this position B, the bottom interface just comes in contact with the particle. Now you can see that at this particular point, the equilibrium contact angle condition is not satisfied, due to which particle is now going to get pulled down, just as for the single interface. But when that happens, now the contact angle condition is not going to be satisfied at either of the two interfaces. Now because the two interfaces are not parallel, they are at an angle, that leads to this restoring force which is going to push the particles towards this equilibrium position. And so that's essentially what happens. As that evaporation takes place, the particle now comes simultaneously in contact with both the interfaces and gets pulled in, but because the liquid is evaporating, the thickness is reducing everywhere, and now the particles are now going to go to that particular location where the equilibrium contact angle is going to be satisfied at both the interfaces. Okay? And you saw that the interference fringes were circles, and so they're going to sit on that circle, and as it's evaporating, those circles are moving out, and they're going to be sitting on that circle and move out. Okay? Now what does this do is also tells us how to determine the contact angle using this technique, because I know the exact time at which the particle just comes in contact, because that's when it just starts to move in, and that would be, from geometry, I can relate the contact angle to the local thickness, and this on the right hand side is a dimensionless expression for the local thickness, goes as r square. I know that once it moves, it collects itself into that ring, so at that instant, that is the contact angle that I have. And so that from geometry I have these expressions. There are two unknowns here. There's a theta e and an h naught. I can therefore determine these angles. So I can use this technique to determine the contact angles of the particles. Very straightforward. We did this for many 50 particles for each sizes. There is a distribution that we find. I only showing only 3 and 5 microns. We have a similar distribution for 10 microns. Some of you might be surprised by the large distribution. In fact, we were also very surprised with the distribution of contact angles. But we find that using other techniques, people in fact have found much broader distribution of contact angles, and they attribute that to some surface heterogeneities, due to which the contact angle, the interface gets pinned on the surface, and so on, and therefore it's not yet in equilibrium. So you don't have an equilibrium contact at all the times. Okay. We've seen this motion. Now that we know what the force expression is, can we therefore predict the motion of these particles? In fact, we can do, because here is the expression for the capillary force that I had shown you earlier. That's what's pushing the particles, and it's going to be balanced by the viscous drag, which is given by this expression. And on the left-hand side, I have mass times the acceleration. Now, the viscous drag now is going to be very complex for this particular problem, because we have part of the particle inside the liquid film and the other part outside. We have the solution by Saffman for a cylinder which is embedded inside a thin liquid film surrounded by a more low viscosity liquid. In that case, the drag would be function of the geometry of the particle and the viscosity of the two liquids. Given the complex nature of this problem, with this part protruding out and this not being a cylinder, what we do is essentially write this expression as pi times the viscosity liquid times the thickness times the velocity times some unknown factor, which we expect it to be not very large or very small. So you can non-dimensionalize this expression. So here is the viscous force, here is the capillary force, here is the viscous force, and here is the acceleration term. In the non-dimensional terms, this k bar, which is dimensionless curvature, is in fact very, very small. So what really is happening is that when it just starts moving, it's going to accelerate for a very, very short time, but then most of its motion when it moves towards the equilibrium position is going to be determined by a balance of this capillary force and the viscous drag. And so you can essentially put this equal to 0, and you can get an analytical expression for the trajectory of the particle. And how does it compare with experiments? So I have trajectories for 3 different particles of 3 microns and 5 microns. We've done this for 10 microns too. There's a fair match between prediction and the experiments. What I'm plotting here is the distance of the particle from that equilibrium position divided by the initial distance. Right? And in fact, you can see it looks like an exponential decay. So in fact, if you go back to the equations that I showed, and you make an assumption that the thickness of the film locally is approximately the same as the diameter of the particle, and the slope of the interfaces does not change very much during the trajectory, you indeed can show that this ratio has an exponential decay with a time scale given by this expression, which is of the order of 0.1 seconds, which is exactly what we see in our experiments. So here's our hypothesis for the stability. The reason we think, at least one of the reasons we think, that when your contact angle is close to 90 degrees, why this should lead to a greater stability. The reason for that is if your contact angles are close to 90 degrees, let's say somewhere around 80 or 80 degrees, it would mean that once the particle bridges both the interface, they should move to the lowest thickness region of the film, because that is the region where the contact angles will be satisfied at both the interfaces. Okay? And that's true for foams, and that's also true for emulsions. For example, here you have a solid stabilized oil droplet with some particles. If there's a fresh droplet that comes in with very low coverage, then the lowest thicknesses would be right here at close to the point of contact, and that's going to suck in the particles there and prevent the two drops from coalescing. Okay? And in fact, as I mentioned before, in fact, that's what people have observed. So, at least some cases, when two droplets come together, they find that particles tend to concentrate there, even though the average coverage of particles is very little. What is the effect of surfactants, you might be amazed. So in our experiments, there were no surfactants. And so we put in an anionic surfactant, SDS. And what it does is, we have negatively charged particles, is that, of course, it will go and collect at the interface with this polar head negatively charged pointing towards the liquid phase, and these chains on the air side. And what happens is, beyond a certain concentration, we see a slightly different motion. We don't see that quick motion coming in, but what you would find is particles just get pushed out, this slow outer motion. They do tend to collect in a ring, but you don't see that particles getting sucked in anymore. And this has been observed before. In fact, what is happening now is that beyond a certain surfactant concentration, the particle gets repelled from both interfaces, and because now the thickness is reducing and it varies, the particle gets squeezed out from the thinner regions into the thicker regions without absorbing at either of the two interfaces. So the interface essentially wraps and squeezes the particle out from the thin regions to outer regions. So this is really a complex phenomena. To understand complete physics, one has to understand the physics of piercing of the interface. It will depend on electrostatics, van der Waals forces, hydrophobicity of the particle. If you now introduce surfactants, the surfactant could absorb at the interface, at the particle, and then complicate the process. I had this slide. I think I'm running out of time. What I wanted to show here is that the motion that we are seeing is not due to interparticle capillary interaction that is taking place. The one particle does not move towards the other particle, but moves towards a particular region. Those who are interested, I can in fact discuss this slide later. So, to conclude, I think we have found a new form of capillary motion, which I think others have not observed. And it occurs even when each interface is flat, but you need the thickness to actually vary. As I explained before, theta close to 90 degrees should stabilize these films. And it so happens that this particular method could also be used to separate particles by size. This method could also be used to determine contact angles of these small particles. So we need to determine what the effect of surfactant is by taking cationic, anionic, and non-ionic surfactants. Thank you very much, and I'll be happy to answer questions.
You mentioned pinning of contact
Right.
lines, but when you did the force balance for the motion of the particle, you simply used viscosity. Doesn't the moving contact line cause you some problems?
Oh, it does, and we have ignored that. So here is the thing. So what we expect is that if you have a particle like this and it's going to be moving, so there is going to be an advancing and receding contact angle, and that is going to change the actual force which is acting on the particle. The particle is moving so fast, and we have no way really to know what exactly the angles are around the particle. We therefore think that this particular fudge factor that we have essentially accounts for those non-idealities.
Referring to the difference between advancing and receding contact angles, but to the movement of the contact line. You know, there's a famous singularity there, very strong, that you have to resolve.
Yeah, so we haven't bothered about that singularity. Yeah.
Any other questions? Yeah, go ahead, Jason.
What sets the point at which the particles first begin to accumulate and which later forms the center of the ring?
Right. So what sets it is that depending on where the particles are present, at the point when the interface comes in simultaneous contact with both the top and the bottom interface is what will lead to that motion. So the particles which are closer to the center is where the thickness is lower compared to outside. So the particles closest to the center is where the motion would start first, and then as the the film starts to thin, other particles get pulled in, and that's what happens.
So if you suspend the film from a ring, you would always be able to keep the center of the expanding particles at the center of the ring?
Depends on the contact angle. So that's what I was trying to say. So if it's 90 degrees or close to 90 degrees, that's essentially what should happen. And that's what we are trying to do now, is to vary the contact angle so that we can have the particles right at the center at all times. Yeah. Yes.
John.
Thank you. I'm puzzled by one aspect of your treatment and
Yes.
in your figures, is that the interface is always flat. It goes with a constant slope through the particle, so to say. And I have no very, I'm not able to produce a very rational argument, but we all have this intuition of the interface changing its curvature, approaching the particle. Does this happen? Or?
Right. So that's the reason that I gave two different arguments. So you could look at it in terms of forces. If you do a force argument, and that's essentially what I gave here. I said that let's say the particle, the contact angle here is exactly where a flat interface should be. In which case, if I say that the contact angle has to be satisfied there, then the interface should indeed curve this way. And then if you do a force balance, you do indeed get a restoring force. That's one way to look at it. The energy argument, which is what I showed initially for the single interface, is different, and what it would say is, well, if I have a flat interface going through, then my contact angle is not the equilibrium contact angle, it's something else. And so thermodynamics would tell me that there has to be a restoring force towards the equilibrium position. So either way, if you take a curved interface and saying that that's where it should be, I get a force. Or if you look at the energy argument of flat interface, I get the same kind of a force.
Could this happen in a transient stage? Or
Sorry?
could this happen temporarily?
Yes, it does. So there are these experiments from Vinny Manoharan's group at Harvard who have asked the question of how a particle adsorbs at the interface. I didn't have time to show that. So what they did is they have this interface, oil and water, and they pull the particle from the bulk to the interface. And what they observe is initially, as when they pull it at the interface, there's a very quick motion where the particle is now trying to reach that equilibrium contact angle. But then after a very short time, it actually slows down, and it takes hours, more than hours, to reach that particular contact angle. And so what they explain that is by they say that the contact, in fact, the interface gets pinned on the surface, and it's slowly now trying to reach the contact, the equilibrium contact angle.
Thank you.
Any other questions? If not, may I ask a question?
Yeah, please.
Mahesh? Last question.
Yeah.
So there's as Jean-Noel said, you assume a slope of the interface. But I mean, I would have thought that very close to the ring, the interface would have reached a flat
Right. So this is
profile.
only schematic. So in fact, it does have a curvature. It's only constant curvature. I have drawn it this way because I thought it's easier to see. But if you recall in the expression that I have for the thickness, right there, it goes as r square. The thickness actually goes as r square. And that's what is used in all the analysis. It's not a flat interface. But you can explain all of this by assuming a flat interface as long as the thickness is varying.